Okay, so in this little demonstration, I wanted to show you the physics of diffraction by using this setup here. So what I have is a slit. It consists of two razor blades, essentially, that I can bring closer and further apart from one another. So I can form a thin slit of a few micrometers in size. And so I can just change the width b of the rectangle function, if you so want, by adjusting the two jaws. And I have a laser here that illuminates this slit. And so now the slit is wide open, and what you see on this screen here is essentially the laser beam itself. It's not diffracted by the slit because it's not touching it, right? So what I'm now doing is now I bring the two jaws together more closely with one another, and then observe what happens to this pattern. So let me just do this now. So what you can see is you can get a pattern where you have a central maximum here, and then you have a minimum, so where the light intensity goes down to 0. Then you have the first order, second order, and so on. So there's several minimas where this function that we're looking at, which is of course a sinc squared function. We're looking at the intensity. So the sinc squared function will have a high intensity in the middle, right? So and the width here we've worked out in the lectures, and you see many different diffraction orders in this direction. Now note that the slit is positioned like this. Note that the slit is vertical. If I rotate the slit, you can see that the pattern rotates too. The pattern is perpendicular to the slit, as in the lecture when we worked out the Fraunhofer integral for this, the Kirchhoff integral and the Fraunhofer conditions for this problem here. Note now, if I decrease the slit size, the pattern spreads out. So as I make the slit smaller, you can see how the central maximum gets broader and broader and broader, so you get more and more and more diffraction. And that is, of course, precisely what the problem is if we image through limited apertures. Is this in the Fraunhofer case? It's pretty good. I mean, the best way to do this is actually putting a lens here. Then I really collect all the parallel light rays that come back from the aperture and project them with the correct phases onto the screen here. But because we are a very long way away from the aperture, because the aperture is very small, we're still pretty good with the Fraunhofer assumptions. The phase of the light, the laser emits coherent light. The phase filling the light field inside the slit is constant. So the Fraunhofer conditions are definitely met in that way too. Note also that we have no diffraction in the vertical direction here, because the slit is very long, so the light is not obstructed in that direction, and therefore it propagates undiffracted. So that is one example that shows you how essentially the Fraunhofer plane is the Fourier plane of the aperture function here. So rectangle here, sinc squared over there, I want to show you one other example. So let me open this again. Let me open the aperture completely. So now the laser beam is just going through. It's very bright. I have this object here. It looks like a transparent slide. You might not be able to see this. Yeah, yes, you can see. So there's this. It's a transparent slide, which I now put into the laser beam over here. And what you see are two orders on the left and right. So what could the Fourier transform of that be? So you see one delta function here, one delta function there, and you see the central order there. What could that be? Well, if we have two amplitudes k at k here and a k over minus k over there, that corresponds to a cosine wave, right? So in the middle is a DC component. So what I have here is in fact a diffraction grating which modulates the phase of the light impinging on it according to a sine wave modulation. So I only get exactly 2 orders. And the modulation pattern must be in this direction, in the horizontal direction. Otherwise I wouldn't get, sorry, the modulation must be, so the modulation is along the horizontal direction and the lines are vertical in that sense, right? So if I rotate the pattern, let me just do that again so you can see this here, hopefully. You can see this here. You can see the 2 orders now rotating according to the pattern, okay? And so here's an exercise for you. The wavelength of this light is 500 nanometers or half a micron. This distance here is 10 centimeters roughly. And the distance between these 2 orders here, this is -1 and +1, is 10 centimeters. So can you work out what the grating period is of this grating here? I hope with this demonstration that what you see is that what you do when you illuminate an aperture or an object with light, with coherent light, then you get a pattern in the Fourier plane that returns essentially the spectrum, the frequency content of the object. Okay, thanks.